Okay, so if you remember, the title of this section is Derivative Rules and Marginal Analysis. Marginal analysis is kind of an application of these ideas to a business and economic sort of context specifically. So we've been dealing with these particular functions over and over again: cost functions, revenue functions, profit functions. All of these have something called, have a marginal version. It's simply what we define their derivatives to be. So if C of X is the cost of producing X items, then we define its derivative C prime to be the marginal cost function. So right now, this is just terminology. We haven't talked about why we think of it or use the term marginal, but let's go ahead and do an example where we're finding one of these. So it says the best foot forward shoe store has a price demand function given by P of X equals negative 0.03x plus 45, where P of X is the price in dollars per pair of Le Bout-On shoes when X pairs of shoes are sold. Find the marginal revenue when 200 pairs of shoes are sold, and then interpret your answer. So marginal revenue, it means we need a revenue function. We're not given a revenue function, but we know how to find it. Revenue is X times your price demand function. So I'm doing X times negative 0.03x plus 45, which is just negative 0.03x squared plus 45x. Okay? A marginal revenue function is just the derivative of that revenue function. It's R prime. I can use the power rule and my sum rule, my constant multiple rules, all of those rules to deal with this because it's a polynomial. I will get negative 0.06x, that's the 2 coming down and multiplying and then subtracting 1 from the exponent, plus 45, that's the derivative of 45x. That's my marginal revenue function. Specifically, we want the marginal revenue when 200 pairs of shoes are sold. I want R prime of 200. That's negative 0.06 times 200 plus 45. And this comes out to 57. It's revenue, so we would be measuring that in dollars. The way that we interpret that, as of right now, the only way we've been interpreting derivatives is as rates of change. So we would say when 200 shoes, pairs of shoes are sold, the revenue, did I spell that right? Yeah, nope, that's fine. The revenue per pair is increasing at a rate of $57 per pair. Now again, remember, we're saying it's increasing at that rate. This is really a little bit more of an approximation, but that kind of leads into this next thing. So we're gonna use these marginal functions for some approximation things. So here, remember that R prime of X by definition is the rate of increase in revenue, or decrease if it's negative, when X units are sold. But the thing is when we're selling a product, we can usually only represent quantities of those products using positive integers. So it doesn't really make sense to plug in like a 0.956 or something into a function like this. Instead, we need to think of these as positive integers. I'm going to use an n to represent that. So suppose I wanted to find R prime of n minus 1, okay? I can take the limit of a difference quotient, but and the numbers in here need to be integers. So if I write the difference quotient for this, it's R of n minus 1, that input, plus h, minus R of n minus 1, that input, all over h. If h is very, very small, then in the sense of being close to 0, then this will be approximately what that derivative is, because the derivative is the limit as h goes to 0. But if h is just close to 0, we get something close to that derivative. But the smallest I can make h, if we're interpreting these inputs to be positive integers, is 1. I can't make it 0.5 or 0.1 or whatever, if we're specifically thinking of these inputs as representing integers. So if I set h equal to 1, then this becomes n minus 1 plus 1, which is just r of n. And then I have this, plugging that in here, r prime of n minus 1 is approximately r of n minus r of n minus 1, all over 1, because again, h is being set equal to 1 here. That gives me this. This derivative is approximately the difference between the revenue of the total revenue earned for selling n items minus the total revenue for selling n minus 1 items. Or in other words, this is approximately, if I rearrange it, I can say r of n, by adding this term over, is approximately r of n minus 1 plus r prime of n minus 1. So in other words, r prime of n minus 1 is approximately just the revenue earned from selling only that nth item. Because if I add it to the total revenue earned for the n minus 1 items that came before it, I get something that's approximately the total revenue for all n items. That's kind of how we interpret these things when we think of them as marginal functions. Okay, so that's kind of summarized here. We can interpret r prime of n minus 1, I'm off screen, r prime of n minus 1, we can interpret as an approximation of the revenue for selling only the nth unit, as opposed to the first n units in total. And that gives us these different interpretations and uses of these marginal functions. So if I want to estimate the cost or revenue or profit of a single item using marginal analysis, then the approximate cost of making the nth item is c prime of n minus 1. That's what that whole discussion was. We described it in terms of revenue, but the same thing applies to revenue, same thing applies to profit. P prime, R prime, whatever it is, of n minus 1 approximates the revenue or cost or profit or whatever it is of that nth item only. The exact cost, so the exact amount that we're approximating up here, can be found this way. If I want to find the cost of the nth item only, I find the cost of producing the first n items altogether, subtract the cost of the first n minus 1 items, because that would leave me with only the cost of that nth item. Similar application for revenue and profit. Okay, and then finally, we showed this middle one for revenue, but if we want to estimate the cost or revenue or profit of a total number of items using marginal analysis, then for example, if we want to find the cost of the first n items, it's the cost of the first n minus 1 items plus the derivative of your cost function at n minus 1. And again, these are approximations. So it's not saying that these are exactly the same, but they give good approximations. In this example here, we're going to show how good of an approximation this is. So there's 4 parts to this, but we're going to do all 4 of them relatively quickly. A company that produces action figures has a weekly cost function of C of x equals 12,000 plus 80x minus 0.04x squared. I want my marginal cost function first. We've done enough derivatives now that I can do this relatively quickly. The constant goes away, goes to 0. 80x becomes 80. Using my power rule here, this becomes minus 0.08x. Okay? Now, I want to do 4 things. Estimate the cost of producing the 551st action figure. So that's this very first thing right here. To estimate that cost, I find c prime of n minus 1, where now n is equal to 555. That is, I want to find c of 550. That's 551 minus 1. That's literally just 80 minus 0.08x, where x, sorry, I meant to plug that in, is 550. That goes into a calculator. You get $36. That's the cost of that 551st action figure. It's pretty expensive, but this may or may not be realistic for this application. Just an estimate though. How do we find the actual cost? Well, that's the cost of selling 551 items all together, or producing them, minus the cost of those first 550, because that would leave you with just the 550 first. This would go into a calculator. I'm not going to write out, I'm not going to plug 551 directly into this, 550 directly into this, and write all of that out. I'm going to let you do that. But this comes out to something very, very close to our estimate, $35.96. Okay, so that's kind of showing how close this estimate actually is. C, how do I estimate the cost of producing 551 action figures? That was from here. So we do C n minus 1 plus C prime of n minus 1. That's C of 550 plus C prime of 550. And I just noticed up here, I meant to write a C prime right there. That's what we were using for our approximation. I found C prime of 550 before, it was 360. I would just need to go and plug 550 into my original cost function, add it to that 36 and see what I get. This gives me an approximation of 43,936. Remember, that's the cost for producing all 551 of those, or at least approximately. Finally, for part D, I don't want the approximation, I want the exact cost of producing 551 action figures. Well, that's literally what the cost function does. So I would just need to plug 551 into my original cost function. But when I do that, that comes out to approximately $43,935.96. Notice how close that approximation was to the exact answer. That's how powerful these marginal cost and profit and revenue functions are. They do a very, very good job at these specific types of approximations. And that's kind of what we're calling marginal analysis. We will do more with marginal analysis once we define some new functions in the next section: average cost, average revenue, average profit. But we need the product and quotient rules in order to handle those. So we're going to save that for the next section.